Chapter 6, Current, Resistance, and Power Supplies. This chapter is broken up into three parts. Current from the microscopic level, resistance, and power supplies. Just as a quick review, let's look at what we did before. As a quick review, we have two pictures of what a power supply does. So if we look at it from the electric field picture, we assumed that we could have two plates, and when I look at these two plates, we set up a uniform electric field. So in other words, on this plate, I'm going to have positive charges, and on this plate, I'm going to have negative charges. And what ends up happening is that we produce an electric field that's constant. As we'll find out in circuits, that can't be true. So if I put a test charge here, it's going to have a motion from the positive to the negative plate. If I plot the electric field picture, we find out that we have a constant electric field. We see here that E is equal to a constant as soon as that power supply is turned on. And of course, what I'm doing here is that I'm plotting the electric field as a function of time. So then we see that we have a curve that clearly shows that the area, not the area, but the field is constant. The preferred picture is the potential field picture. And the reason why it's preferred is because of conservation of energy. And so in a very analogous way, we have two plates, but one of these plates is higher up than the other one. So if this is my higher and this is my lower, we then say that we have a low potential here, and then up here we have a high potential, where again we have charged plates. So the battery is represented by this incline. And so what's important about this is that this height is the height of the battery, which we call the source of the energy, where this guy is, of course, grounded. So if I place a test charge here, then we can visually say that in this electrical space, the charge moves from high to a lower potential. And the reason why we get this picture here is because if we plot the potential field as a function of position, we saw that you get the electric field times position. And as a consequence, we then have an electrical ramp where we then come in here and we say that this guy represents the potential landscape. As a function of position, of course. So once again, if I place a test charge, it just slides down that incline. But there's another thing that we said about potentials, is that if there was no potential, then we could have then, let's say if I copy this right here. So if I had two potentials that have the exact same charge, okay? So if I look at this here, and I have the exact same charge, in other words, the charge difference between these two is not the same, we're going to find that the potential here is flat. So if I place a test charge here, that test charge is not going to move anywhere. On the other hand, if I have a plate that's highly charged, on the other hand, and I put this guy here, and I can also say that if I look at this flat plane, and I have a test charge right here, then this test charge would have no motion. Even if this thing was at 1,000,000 volts and this was at 0 volts, we would find that here and here there is no force acting on this charge. That doesn't mean that the charge is stationary. It just means that there's no net motion. And we'll be a little bit more careful in a moment here. So in summary, we say this: if we have a potential difference that implies that the voltage is not equal to 0. And as a consequence, we have charge motion, which means that we have current flow. If we have no potential difference, then that means that the voltage here is equal to 0. That tells us that there is no current flow. So the bottom line is, this is what we have to bank on as we start to analyze everything in the near future. Now let's go to what we're trying to talk about. We want to talk about our lecture here, which is 6.1, is on microscopic currents. And frankly, I find this lecture to deal with many misconceptions. And so our goal here is to try to dismiss some of these misconceptions and move on. So before we get into microscopic currents, we need to correct one so-called fact about conductors. Because we didn't say this, but we have to say it now. So the first thing that we want to do is that we want to look inside a perfect conductor. As we know here, wires are the highways of electric charge. and the wires have been assumed to be perfect conductors. Well, unfortunately, that can't be correct. Wires are the highways for electric charge. And are assumed to be perfect conductors. Unfortunately, this cannot be correct. So why is this? Inside perfect conductors, the fields are zero. In other words, we have the electric field inside a perfect conductor is equal to zero due to polarization, or the voltage delta V is equal to zero. So that means here that charges can't move. So if I look at this picture here, you could imagine that I have a wire, and the most obvious choice is to pick a copper wire. So here's my copper wire right here. And so if I take this copper wire, what I'm going to do here is that I'm going to place a test charge in here. So what happens to a test charge in a perfect conductor? So I'm going to need this, so I'm going to move this over here. So here's what we find. In a perfect conductor, the electric field is zero inside. That means the electric force is zero. So no force will act on the charge and move it. That's a problem. How are you going to get current to actually move through a wire? In a very analogous way here, what we find here is that we have flat potential functions in here. And because we have flat potential functions, that means here is so a flat potential landscape shows charge will not move. Once again, for any charge, inside a perfect conductor, no motion will ever occur, because there is no push to propel the charges forward. Therefore, a charge that does move will have a net displacement of 0 and 0 current. So in summary, a perfect conductor will have no directional current that can actually move it. So, however, in real life, there are no perfect conductors at room temperatures. And the reason why room temperatures are important, you can have high temperatures superconductors, but we're not interested in that. We're talking about regular circuits that you have in your cell phone or wherever. So they don't exist for our purposes. So now let's talk about inside a real conductor. Real conductors are imperfect, are not perfect, and can have non-zero small voltages inside wires. In other words, the potential inside is close to 0, but not 0. The electric field inside is really small, but not 0. And as a result, current can't exist. Now, current is a superposition of two types of motion. One of these motion is what I would call the randomized motion due to collisions. And then the second one is a directed electrical motion due to potential differences. So let's look at that. So let's first start talking about randomized motion. So what I said here is it was due to collisions. So what we do here is that we have to draw a wire, let's say a copper wire. So let's sketch a copper wire. So if I sketch a copper wire, what I imagine is something like this. So if you look at a copper wire, the color is more gold. Note a very interesting question, which I will not answer, is why are most metals silver gray, but copper is this gold color, this orange color, red-orange color? It's a great optics question. So here's what we know. I have in copper wires, I'm going to have ions, copper ions. And when you look at these copper ions, they turn out to be gigantic. So let's say that these blue copper ions here, because they have lost an electron or so, they're now positive ions. So then right in here, I'm going to say that this guy right here, this is a copper ion fixed in place. In other words, they cannot move. But on average, let's say that each copper atom has one electron associated with that copper atom. So then I would say here is that these guys right here, these are the weakly bound / conduction electrons. So if we start to deal with this question here, is that imagine that we have an electrostatic. So the first thing I want to do is that we're talking about randomized motion. So that means that the wire has to be an electrostatic scenario. So in electrostatics situation, for the wire, the voltage across the wire is 0 everywhere. And no net current can exist. We got to be careful about that. That word net current is a tricky word. However, some electrons in conductors are free to move randomly. At extremely high speeds. Now, these speeds are high. The number that I remember, but it's only an order of magnitude calculation, is 1 million meters per second, which is about 2 million miles per hour. And if you look at what that means, that's about 600 miles per second. So these numbers are crazy. I think they have measured electrons and conductors at room temperature to be of the order of 3 million miles an hour. It doesn't really matter. The number that's most important is 10 to the 6 meters, 1 million meters per second. The issue here, the core issue here, is these electrons will have a massive number of collisions with the copper ions. As a result, this causes the electrons to have a randomized motion that effectively goes nowhere. It goes nowhere. That is, the electrons average displacement is 0. That's what I mean when it says it goes nowhere. So you could imagine that here's my electron right here. So now what happens is that you know that there are a bunch of copper ions. So maybe it comes up, it collides one, then it shoots this way, it collides with another one, it comes up here, it collides with another one, and you could just see here that I'm just going to get some zigzag motion that's just moving around. But the bottom line here is that the electron effectively ends up in the same place. So once again, right in here, we could say that it effectively starts and ends at the same place. This motion is what I call the randomized motion caused by collisions. I mean, you got to think about this a little bit more, right? I find this astounding. You know, effectively, we could say here is that the electron is all dressed up. But nowhere to go. That's effectively what is happening. That is, until a friendly neighborhood electric incline comes by. Now we are at directed electrical motion. As soon as we have directed electrical motion, things change. So if a small voltage is applied across the wire, the electrons now have directed motion caused by the incline. So again, there's two pictures. So if I think about my copper wire, let me see if I could come in here and grab my copper wire. Oh, that's a bit too big. Let's not make it this big. Let's redraw it. So I imagine that we have our wire. So let's say this is our wire right here. And we're coloring it this yellow because we're kind of guessing that it's a copper wire. So now I have my ions. So I have my ions here, here. So my copper ions are here. And what we're seeing here is that we are now placing a voltage across that. In other words, I'm setting up a low potential here, and I am setting up a high potential here. So when I have that, now I have my positive charges that are now going to start moving. So I look at these guys, and these guys now have motion. And the reason why they have motion here is because now we have a voltage inside that's not zero. But I prefer a different picture. So the picture that I would prefer, I imagine that I have an incline. And this incline has a particular height that's due to the source. So now if I look at these charges, we know that down here is our low. We know that up here is our high. So now charges could start moving. So if I start to look at these charges, I have to draw in my copper ions. And at the same time, I have to draw in my my charges. So now as this thing is moving down, we see that we have motion. There's a net motion now causing these guys to go down the incline. So what we call current is a superposition of randomized plus directed motions. So if I look at my picture, I really have this picture. let me steal this guy right here. So if I copy this, I now have my randomized motion right here. That's my randomized motion. At the same time, and that just tells us here that inside, this is still 0. Now I have an incline. And if I have an incline, then we know here that this guy sets up a voltage inside, and it increases the height. And of course, we have low, and now we have high here. So if I go look at my charge, that charge can now start moving. And as it moves, it's going down the incline. So if I look at these things, and if I add these together, look what ends up happening. I still have this random motion. But now, when I look at this guy, you are seeing that motion is now moving here. It's moving in this direction. And so what we say here is that this motion we call VD, and this VD tells us that VD is not equal to 0 and is called the drift speed. So the whole thing moves with this drift speed. Now, there is a really good analogy to think about. Okay. So the one thing that you want to think about is I think this is a really good analogy. And we have this, of course, in the lab at Cabrillo, but the best analogy is a modified pachinko machine. Now, this is a Japanese game, but if you modify it, it is super useful for explaining this. So you could see I have pegs, right? So right in here, you could see that these are the pegs. And we'll say that these pegs are actually the copper ions. And then this height right here, inside the wire, there's a voltage set up by the battery. So now what starts to happen? Well, you can see that if I drop a peg, a ball, it's going to collide. And as it collides, this one's going right through here, it's actually moving in a random direction until it moves out. So a couple of things. So the first thing that I would say is that if there are no pegs, copper ions, electrons move at 1,000 meters per second. Remember, that's about 2 million miles per hour. That's pretty damn fast. With the pegs, there are two motions. One of them is that the peg collisions cause random motion. The second thing here is that the electron drift, in other words, the directed motion, is caused by the incline. In other words, inside there's a small voltage that's not equal to zero. So if I was to try to draw a better picture, let me see if I can do this guy right here. Okay, I'm going to copy these and then I'm going to modify these. So here we go. I might just need a bigger picture. So what I'm seeing here is that in this case, I'm going to say that this is randomized motion. So I need to come in here and I need to get rid of these guys right in here. So there is motion, but we'll talk about this in a moment. But there's no directed motion. So right in here, I'm going to say that we have random motion. And as we said before, random motion deals with collisions. So you could imagine that I have some of this scenario here where now I have a positive purple charge. And what we're seeing here is that this guy now starts colliding and it effectively goes nowhere. So our point here is that we focus on collisions to describe motion. Now we put a potential difference across this thing. So in this case, we have a high and we have a low. And even though I didn't write this, I should have. The voltage inside of this thing is zero. It's all because these guys have, an internal speed of about 1,000,000 meters per second. Now, if I add these two, this is going to be the directed motion. So now I have this. And so what happens now is that now the charges start to move down. So if I look at this thing, this is going to equal to this. But now what I have to do is I have to come back and I have to modify this. So the way I'll modify this is that I'm going to focus only on one charge. And this charge that I'm going to modify, that I'm going to look at, it's going to be this guy right here. So what happens here is that that charge now is now going to go after many, 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 many collisions before it actually makes it down. This right here is what we call electric current. And I'm going to have to move this down. That's what we mean by that. Now you can see how, if we looked over here, if I was to look at this modified Pachinko machine, well, it's a randomized process. So one of the things that I could do, if I start here, it could have bounced here instead. And maybe this guy bounces here and then bounces here. and then bounces here, and then bounces here, and then bounces there. So you get this randomized process that starts to occur. Maybe I drop it in the exact same spot, but now the charges start moving something like this here. So the outcomes change. And because they change here, you can have a variation of paths. Electrons do not take one particular path. To emphasize this, there are computer Monte Carlo simulation models of current flow inside real conductors. And I'll tell you one thing, we have to ask the question, is this art or is this science? If you ask me, it's both. It's absolutely both. So what does this do here? So this thing represents the possible paths of charges. Now look what I can do here. What I'm going to do is I'm going to focus on one charge. So I'm going to follow the charge right in here, and I'm going to follow this path. So now, just like we saw on this Pachinko machine, that there's a spread, even though they started at the same spot, what you're seeing here is that now there's a range of possibilities. In other words, this guy right here is telling you of the possible paths. So this guy tells me about, I don't want to write in here, but this tells us about, so it represents the possible outcomes of electron paths. That would be one of them. What about this guy? If I follow this one over here, you could see that I follow it here, and then I come to about, it looks like it gets to about right here, and then all of a sudden it looks like it's spreading right in here. So I'm seeing here numerous possible paths. Beautiful images or current. Now, we want to talk about one last thing here before we finish off, is that we want to do an energy analysis of current. And this will be the last thing that I do. The electron at the top of the electrical incline is all potential energy. So an electron at the top of the electric incline is all electrical potential energy. We don't have to do that. I'm just assuming that the initial kinetic energy is zero. I don't have to do that. It just makes it easier. So as the electron makes its way down, the numerous collisions keeps the speed, and earlier I called it a drift speed. It keeps the speed constant. And that's unbelievable. It keeps the drift speed constant and therefore does not increase kinetic energy. In other words, the change in kinetic energy is zero. Where does all the energy go? The electrons transfer its electrical potential energy into microscopic kinetic energies of the copper ions. There's a tiny portion that goes to other electrons, but it's tiny, which is called heating. In other words, this results in copper wires increasing in temperature. So I'm going to say that a lot of people have a misconception. So I'm going to say that some of you will have a misconception about the charge. It's common for students to think the electrons transfer electrical potential energy into kinetic energy of the electrons. Well, that's simply not true, since the change in kinetic energy is zero. Most of the most of the electrical potential energy goes into heating up the conductor, not making the electrons move faster. Some of this energy goes into other forms. It could go into sound, light, or whatever. So let's talk a little bit about charge carriers. We've already talked about this briefly in chapter 5, but let me just verbally say it. Excuse me. Different types of materials have different charge carriers. Metals have negative charge carriers, but you can have ionized gases that have both negative and positive charges. We talked about the conventional current flow, which means that that's the motion of positive charges. The electronic current is about negative charges. So one of the things that's important here is that the drift velocity cannot be a vector because electrons have random directions due to the frequent directional changes by the collisions. Because the drift velocity is not a vector, the current cannot also be a vector. So the only direction that you can have is the direction of the incline. And one last thing. We know that in metals, the charge carriers are the electrons, not the positive ones. As we said in the previous chapter, the choice of defining what is positive and negative is arbitrary and does not affect any of the physics. Usually the blame for assigning the charge carriers as negative, that it fully falls on Benjamin Franklin. History is never black and white or gray. No, but gray. One also must include Galvani and Volta, since they already assigned the polarity of a battery. And this had a role in Benjamin Franklin's choice.